This lecture video is about the derivation of the Nernst equation. The Nernst equation derivation relates single electrode potential. Single electrode potential is denoted as E, and change in free energy delta G, and concentration is denoted as M power n plus. That according to thermodynamics, the decrease in change in free energy, that is minus delta G, equal to maximum amount of work that can be obtained from a chemical reaction. So this maximum amount of work, that is equal to number of coulombs into energy available per coulomb. Number of coulombs, that is equal to NF. N is nothing but number of coulombs and energy available per coulomb. This together we name as a number of coulombs. Energy available per coulomb is the cell potential. It is denoted by capital E. Here you can see energy available per coulomb. It is given in the box, that is denoted as E. So now we can write the W max value, that is equal to NF into E. So N into F into E. This is represented in the equation 2. So the Nernst equation based on the decrease in change in free energy, that is equal to W max. The W max value is given here, that is a NFE. The first formula, equation number 1, it is substituted. So now we can rearrange the above equation and it can be denoted as delta G equal to minus NFE. The negative sign minus is shifted in the opposite side. This is represented in the equation number 3. Under standard conditions, the same equation number 3 can be rewritten as delta G naught, that is equal to minus NF E naught. So what is this E naught? E naught is standard electrode potential. Standard electrode potential is the potential when a metal is dipped in 1M solution of its ions, or when an inert electrode is in contact with a gas at a pressure of 1 atmosphere at a 298 Kelvin. So now Nernst equation we are going to derive for the reduction reaction. Here we have taken Mn plus n electrons, okay, and it is in a reversible reaction and it gives M. This type of the reduction reaction only we have to take for deriving the Nernst equation. So here we are going to relate the delta G and delta G naught value by taking the want of equation. The equilibrium constant Kc is related to change in free energy. How to denote change in free energy? That is denoted as delta G by want of equation. So now down here we are represented the want of equation delta G, that is equal to delta G naught plus RT ln Kc. The Kc value is given based on the above equation, that is a reduction equation. Kc, that is equal to M by Mn plus. That is a product by reactant. Product is M and the reactant is Mn plus. So now we have to substitute that Kc value. Here in the side you can see the Kc value that is substituted in the want of equation. Delta G equal to delta G naught plus RT ln Kc value is M by Mn plus. So we have to rewrite the next equation, delta G, that is equal to delta G naught plus RT ln M. Okay, instead of divided by Mn plus, here it is written minus RT, okay, ln Mn plus. It is given the equation number 6. So now we have to move for the next step, substitution of the delta G and delta G naught value. Delta G value is minus NFE, delta G naught under standard conditions, it is minus NFE naught. So now RT ln M, remaining things, keep it as it is. This entire equation is named as a 7th equation and we have to divide this entire equation by minus NF. So the next thing is dividing the entire above 7th equation by minus NF. You can see here minus NFE divided by minus NF equal to minus NFE naught divided by minus NF plus RT ln M divided by minus NF minus RT ln Mn plus divided by minus NF. The equation number is 8. The next one, by cancelling all the terms, I'll move back for the previous equation. In this equation, we are cancelling. If we cancel, this one I can show here, cancelling the terms of your NF get cancelled. Okay, minus NF get cancelled, and minus NF get cancelled. And here RT, when we keep the concentration of M is equal to 1, this entire term also get cancelled. This entire term get cancelled. Then minus into minus plus comes, and RT divided by N. Then we have to move for the next one. Cancelling all that, we'll be getting the next equation. Cancel all the terms, and we'll be getting the next equation. So now we are moving for the next step. E equal to E naught plus RT divided by N ln Mn plus. This is denoted as ninth equation. Substitute the values for the RT and F. F value we can substitute here. It is given R value 8.314, T value is 298 Kelvin, and F value is 96,500 coulomb per mole. Very important note, E equal to E naught plus ln to log conversion. So when we are doing ln to log conversion, introduce 2.303 RT divided by NF log Mn plus. So this is given the number 10th equation. This is named as a Nernst equation for the single electrode potential. So after substituting all the values, this entire RTF value, finally will arrive with the final equation E equal to E naught plus 0.0591 divided by N log Mn plus. This is the equation for the single electrode potential. When we move for the cell potential, the same E equal to E naught plus 0.0591 divided by N log, instead of Mn plus, we have to write reactants by products. So here again one more term E equal to E naught plus 0.0591 divided by N log species at cathode side of the metal ions divided by anode side, species at anode. This is a way of representing the cell potential. So now we'll move for the problem based on the single electrode potential and for the cell. The problem here is calculate the electrode potential of copper at 25 degrees Celsius when it is dipped in 0.015 m copper sulfate solution. Given SRP of copper is 0.34 volt. This is the given problem. For this, we'll start with the formula, general formula, Nernst equation for the single electrode potential. This is a single electrode potential equation, E equal to E naught plus 0.0591 divided by N log Mn plus. Substitute the values. What is the E naught value? Look into the problem and substitute 0.34 and 0.0591 and Mn plus copper sulfate, Cu2 plus SO4 2 minus. So we are substituting the N value is 2. Log and concentration of Mn plus ion is 0.015 m. So it is given in this substitution. Already it is substituted 0.015. The answer, final answer is E cell, that is equal to 0.296 volt. So after substituting, and if you do log value, everything, if you take, the final answer of this E cell value is 0.296. This is one type of problem. Only one concentration is given, so that we are selecting the single electrode potential equation. When we move for the second type of the problem, this is second problem. A galvanic cell is obtained by the combination of iron rod immersed in ferrous sulfate solution of concentration 0.25 m and copper rod immersed in copper sulfate solution of concentration 0.45 m. Give the cell representation, cell reactions, and calculate the EMF of the cell at 30 degrees Celsius. It is not 25 degrees Celsius. Note down this 30 degrees Celsius. Given that standard potentials of copper and iron electrodes are, these are the two different electrode potentials, that is 0.34 volt and minus 0.41 volt respectively. So for this type of problems, two different concentrations are given. Okay, so we have to move for the cell potential equation formula. Cell potential equation formula. The cell denotation is this is a cell notation. It is given as a Fe slash Fe2 plus double slash Cu2 plus slash Cu. So based on this, you can see which metal can act as an anode and which is acting as an cathode. So here iron is acting as an anode because the reduction potential given in the problem is minus 0.41 volt. So for the next metal, that is in copper, it is acting as a cathode. So based on the reduction potential value, the metal which is lower potential is fixed at the anode side. The metal which has a higher potential is fixed at the cathode side. So now we'll move for the solution. So here the anode and cathodic reactions are there. Fe gives Fe2 plus 2 electrons. At the cathode side, Cu2 plus accepts 2 electrons and gives Cu. Cancel the common terms, that is 2 electron, both the side, and we'll get the net cell equation. So this is a formula for the cell potential. So before solving that, we have to find out E naught value also. E naught, that is nothing but simple EMF formula, E cathode minus E anode. So with that, plus 0.0591 divided by n log of whatever the product you get here, Fe2 plus Ceo. That should be written here, and this is the reactant value we have to write. Then substitute the values 0.34 minus 0.41 plus 2.303. Since the temperature is 30 degrees Celsius, we cannot take as it is 303. 273 plus 30. If you add up, you will get 303. The remaining R value, 8.314 divided by 2 into 96,500 log term. This is the concentration of the cathode by anode. Cathode concentration, you can see the problem 0.45. Anode concentration is 0.25. So by completing all this, you will get the answer 0.764. So this is how you have to solve the problem for the Nernst equation.